generalized NAND structure with multiple inputs. At this point, we expand our analysis to generalized N-input NAND gates, which consist of N-series connected driver transistors as shown in figure, neglecting the substrate bias effect and assuming that the threshold voltages of all transistors are equal to VT0. The driver current ID in the linear region can be derived as an equation, whereas VD in saturation is taken as its extension. RD equal to nu n C naught S by 2 1 by summation K on 1 by WL K 2 Vn minus Vt naught V out minus V out square linear V in minus Vt naught square saturation. Here you can see in this figure the generalized NAND structure and its inverter equivalent. Hence the WL ratio of the equivalent driver transistor is WL equivalent equal to 1 by summation K on 1 by WL K if the series connected transistors are identical, that is WL1 equal to WL2 is equal to so on equal to WL, the width to length ratio of the equivalent transistor becomes WL equivalent equal to 1 by N W by L. The NAND design strategy which emerges from this analysis is summarized as follows. For an N-input NAND, first we determine the WL ratios for an equivalent inverter that satisfies the required VOL value. This gives us the driver transistor ratio WL driver and the load transistor ratio WL load. Then we set the WL ratios of all NAND driver transistors as WL1 equal to WL2 equal so on and WL driver. This guarantees that the series structure consisting of N driver transistors has an equivalent WL ratio of WL driver when all inputs are logic high. For a 2-input NAND gate, this means that that each driver transistor must have a WL ratio twice that of the equivalent inverter driver if the area occupied by the depletion type load transistor is negligible. The resulting NAND 2 structure will occupy approximately 4 times the area occupied by the equivalent inverter, which has same static characteristics. Note that large WL ratios will also result in large parasitic capacitance. Transient analysis of NAND gate. Figure shows a NAND 2 gate with all parasitic device capacitances as in the inverter case. We can combine the capacitances seen in figure into one lumped capacitance connected between the output node and the ground. The value of the lumped capacitance C load, however, depends on the input voltage conditions. Assume, for example, that the input VA is equal to VOH and the other input VB is switching from VOH to VOL. And in this case, both the output voltage Vout and the internal node voltage Vs will rise. The resulting from C load equal to C GD load plus C GDA plus C GDB plus C GSA plus C G plus C DBA plus C DBB plus C SBA plus C SB load plus CY. Note that this approximation fully reflects the internal node capacitance into the lumped output capacitance C load, and this is quite conservative. In reality, only a fraction of the internal node capacitance is reflective into C load. The use of overly Here in this figure you can see parasitic device capacitances in the NAND 2 gate. Conservative capacitance values in the design will lead to a conservative speed estimation and force the designer to increase transistor sizes to counter the expected large delays. Now consider another case where VB is equal to VOH and VOA switches from VOH to VOL. In this case, the output voltage Vout will rise, but the internal node voltage Vx will remain low because the bottom driver transistor is on. Thus, the lumped output capacitance is C load equal to C GD load plus C GDA plus C DBA plus CSB load plus C wire. It should be noted that the load capacitance in this case is smaller than the load capacitance found in the previous case. Thus, it is expected that the high to low switching delay from signal B connected to the bottom transistor is larger than the high to low switching delay from signal A connected to the top transistor. Thank you.